Let's start with a quiz prep. What are the main processes driving the densification of snow? There are 4 different answers here, possible answers. I'll let you read through that. And so the right answer for that one is answer B. And we go through the other answers to see why. First answer A, compaction, calving, glacier advance. Those two last processes, calving and glacier advance, have nothing to do with the densification of snow. Compaction, melting, and refreezing are processes that are associated with metamorphism. So this answer is correct. Percolation could be a process that plays in the densification of snow, meaning that you have some water that is percolating, is going through your snowpack. That could increase the density of your snowpack. But the thing is that thinning and glacier retreat have nothing to do with the densification of snow. Finally, geothermal heat and densification. Well, that answer is just wrong because well, you see why it's not as precise as answer B. That's really stating out the main actors. So what keeps a glacier alive? Glaciers are always striving to find a balance between accumulation and ablation. If you have a lot of ice that is being created, your glacier will advance. And at some point, it will stop advancing and kind of reach what we call a steady state, where it kind of stays there and doesn't do much, doesn't retreat or doesn't advance. If a glacier is losing more mass than it is creating in its accumulation area, then the glacier retreats. And those processes are called accumulation. So any addition of snow or ice into the surface of the glacier, or ablation, which is the removal of snow or ice from the glacier, from the surface of the glacier. Accumulation can have 3 different processes. So snowfall, as we talked about, wind drifted snow, meaning that let's say you have a mountain that's close by and wind is blowing the snow from the mountain onto the glacier. That's going to count as accumulation. You can also have avalanches falling on glaciers, so that brings new material. That's also accumulation. In terms of ablation, we have melt, especially with the sun shining on the ice. We have wind erosion. That sounds a bit weird, but wind, when it's really strong, can actually take some of that material away from the glacier. Calving, where icebergs break off from the main glacier and therefore we lose that mass. And sublimation, which is ice that actually is not melting but going directly from solid to gas. And those processes, ablation and accumulation, those mechanisms, as I said 2 videos ago, are determining where the equilibrium line is. The equilibrium line corresponds to the transition between accumulation and ablation on your glacier. If you have an equilibrium line that is very low on the glacier, it means that the glacier has a big area that's creating mass. So it's probably going to advance. If you have an equilibrium line that is high in altitude, it means probably that the ablation area of your glacier is bigger than the accumulation area, and therefore the glacier might undergo a retreat. So accumulation zone is just where the snow accumulates. Ablation zone is where the snow melts, and the equilibrium line is where you have as much snowfall as you have snow melt. That's where you're not gaining or losing any ice mass. And that moves from year to year, season to season. It's a very important concept because it kind of tells us from just a glance of how well a glacier is doing. Is it melting a lot? Is it accumulating a lot? That is a very precious information. In real life, this is what the ELA, or equilibrium line altitude, looks like. That is represented in the dashed red line here. We can see below that the ice is really outcropping. It's apparent on the surface, meaning there's no snow on that ice. The snow melted away. And above that dashed line, we see mostly snow. meaning that, let's say this picture was taken at the end of the summer, we have snow that survived the whole summer, so it's firm, and we can expect it to become ice after a few years. So that's where the equilibrium line is. It is not always the case. Sometimes you can have a snow line, but it's a bit more complicated. But without going into a rabbit hole, the presence of snow doesn't always tell you where the equilibrium line of the glacier is, but it's a good indicator still. And now if we talk about mass balance is probably the most important concept in glaciology. It tells you how the glacier is doing, how the total amount of ice is changing through time. We are talking about net mass balance, which is the difference between accumulation and ablation. If you have more accumulation than ablation, so the glacier is creating mass, it's creating more ice than it is melting away, then that net mass balance will be positive. If the glacier is losing more ice than it creates, then that net mass balance will be negative. If you look at so you can think of the mass balance in terms of the entirety for the entirety of the glacier, but you can also divide your glacier into smaller sections. Let's say that we divide our glacier into its accumulation area and ablation area. In the accumulation area, you will make more ice than ice that will melt away, so the net mass balance is positive. In the ablation area, that's the opposite, and the net mass balance is negative. And at the equilibrium line, and that's a very important concept, the net mass balance is 0 at the equilibrium line. If you look over the years, over 1 year, sorry, you can even divide a bit further that concept of mass balance and net mass balance. We can talk about winter balance and summer balance. On this drawing here, the winter balance is represented by the blue arrow, and the summer balance is represented by the red arrow. The net balance, which is the difference between the blue and the red arrow, is represented by that green arrow. So let's take the top case of that figure. It's winter. You have time here on the x-axis, on the horizontal axis, and the amount of change of the snow and ice in meters here on the y-axis. So it was a pretty snowy winter, and at the peak of winter, at the end of winter, sorry, you have that much ice, that much snow, sorry, on a glacier, so around 2 meters. It's the end of winter, we are entering summer, and at the end of summer here, where you have the red arrow, we lost 1 meter of snow. It means that the net balance for the glacier during this year was plus 1 meter. It was a positive number. We created more ice than we lost. And that snow that survived the summer here is considered to be firm. And you can see here more snow starts accumulating in the next winter. If we take, so that is typical of the accumulation area of a glacier. Now let's take the case where we are in the ablation area. We have some snow that falls on the glacier, not that much, approximately half a meter. Winter ends, half a meter, yeah, sorry, winter ends, and we are starting to melt that snow away. Eventually, all of the snow accumulated in winter has melted away, but you can still melt some ice. So you're melting the ice over and over, and you end up with approximately 1.5 meters of ice that melted away. So because you had more melt than accumulation, the net mass balance for this time is negative, and still the difference between those two arrows. So there are 3 possible mass balance scenarios when you look at a glacier. If the equilibrium line altitude is near the top of a glacier, it means that most of the glacier is experiencing ablation. So you have more melt than accumulation, therefore the glacier loses mass. In that case, the terminus of the glacier will retreat. The glacier will undergo retreat. If we take the opposite case where the equilibrium line altitude is close to the bottom of the glacier, so a very low altitude, then most of the glacier is experiencing accumulation than melt. Therefore, you have a very positive, a very positive net mass balance, and the glacier will advance, its terminus will advance. The terminus is where the glacier ends. I don't know if I specified that. Then you have a third case, which is the ELA is around the center of the glacier. So about half of the glacier surface is experiencing melt and the other half is experiencing accumulation. Therefore, melt is equal to accumulation over your entire glacier. So the glacier is stable, or we say it is in equilibrium or at steady state. The terminus is staying at the same location. Those are very important key processes that will be on the exams, so make sure you know all of that.